9 minutes. That is how long it would take the Orion capsule returning from the moon to travel from New York City to London if it were heading in that direction instead of toward the Pacific Ocean. Not 9 hours, which is what a commercial jet requires for that same journey. Not 90 minutes, which is how long the space shuttle took to orbit the entire Earth. 9 minutes. The distance between two of the largest cities on the planet, separated by 3,459 miles of Atlantic Ocean, covered in the time it takes most people to decide what to order for lunch. The number sounds wrong the first time you hear it. It sounds like an error, like something that was stated incorrectly and needs to be walked back with the correct figure. It is not an error. On the morning of April 10th, 2026, the Orion capsule named Integrity hit the Earth's upper atmosphere at 25,000 miles per hour. And for the 8 minutes that followed, it was the fastest crewed vehicle in the history of human spaceflight. Faster than any military jet ever built. Faster than any missile currently in any arsenal on Earth. Faster than the sound of its own passage by a factor of 32. At that speed, the distance between New York and London is not a journey, it is a moment. A brief interruption in something larger, a geography that exists and then is behind you before your body has processed that it was ever ahead. This is not a story about speed as achievement. Speed as achievement is for record books and press releases, and this story is not about either of those things. This is a story about what 25,000 miles per hour actually is. What it does to air, what it does to metal, what it does to the 4 human bodies that were inside the metal when it happened, and why the fact that those 4 people are alive to describe the experience is not a foregone conclusion, but a specific, engineered, narrowly maintained outcome that depended on physics being understood correctly, and materials performing as predicted in an environment that cannot be fully replicated on Earth. The Artemis 2 mission had been in space for 10 days when the crew of Integrity began their final approach to Earth. Commander Reed Wiseman, Victor Glover, Christina Koch, and Canadian Space Agency, astronaut Jeremy Hansen had flown farther from Earth than any human beings in history, 252,000 miles, breaking a record that had stood since Apollo 13 in 1970. They had orbited the moon. They had seen the lunar far side. They had become, briefly and formally, the most distant humans in the recorded history of the species. And now they were coming home. The mission was complete. The dangerous part, most people watching from the ground assumed, was behind them. But here's the problem. The most dangerous part of the Artemis 2 mission was not the launch, which generated enough thrust to move 5.75 million pounds of rocket off the ground and into orbit. It was not the translunar injection burn that sent the capsule toward the moon. It was not even the maximum distance record. Though the radiation environment at that distance, and the absence of any rescue option in any direction, made it genuinely life-threatening in ways that the word record does not convey. The most dangerous part was the last 8 minutes, the return. The moment when 10 days of careful, precise, deep space operations reduced to a single violent transaction with the planet they were returning to, a transaction conducted at the speed that transforms the air of an atmosphere into something that should not be able to exist near a living person. 25,000 miles per hour requires context to mean anything. The fastest production car ever built reaches a top speed of approximately 300 miles per hour. It would take that car nearly 4 days of continuous driving at maximum speed to cover the distance that Integrity covered every hour during peak reentry. The SR-71 Blackbird, the fastest air-breathing aircraft ever flown, reached a top speed of approximately 2,200 miles per hour. It is the aircraft that most people think of when they think of extreme speed, the benchmark for fast in the atmospheric flight context. Integrity was traveling at more than 11 times the speed of the fastest plane ever built. Not faster. 11 times faster. The comparison is not meant to be impressive. It is meant to establish what the air experiences when something moving at that speed enters it. Air at normal speeds is cooperative. It moves out of the way. It flows around obstacles, creates pressure differentials, generates the lift that keeps aircraft in the sky and the drag that eventually slows everything down. At 25,000 miles per hour, air does not have time to be cooperative. The molecules cannot move out of the way fast enough. They get stacked up in front of the oncoming object in a compression that is not gradual but essentially instantaneous, and that compression generates heat through a mechanism that is not friction. in the conventional sense, but something more fundamental. When you compress a gas, you do work on it. That work transfers to the gas's thermal energy. The faster the compression, the more thermal energy. At 25,000 miles per hour, the thermal energy generated in the shock wave ahead of the Orion capsule raised the temperature of the surrounding air to approximately 18,000 degrees Fahrenheit. And this is where things change. 18,000 degrees Fahrenheit is nearly twice the temperature of the sun's visible surface. The sun, the star that this planet orbits, the source of all light and heat that has sustained every living thing that has ever existed on Earth, has a surface temperature of approximately 10,000 degrees Fahrenheit. The shock wave ahead of integrity was nearly twice that, not in a laboratory, not in a simulation. In the actual atmosphere of the actual Earth, 75 miles above the actual Pacific Ocean, surrounding a capsule containing 4 actual human beings. On the morning of April 10th, 2026, that air did not touch the capsule directly. Between the shockwave and the outer surface of Integrity's heat shield was a thin layer of relatively cooler gas, a boundary layer that exists because the shockwave stands slightly ahead of the vehicle rather than colliding with it. The heat shield surface itself reached approximately 5,000 degrees Fahrenheit, which is roughly half the temperature of the sun's surface and still several times hotter than the melting point of steel. The heat shield did not melt because it was not made of steel. It was made of avcoat, an ablative material specifically designed to absorb thermal energy and char, to convert its own molecular structure into gas and carry the heat away in the slipstream rather than conducting it into the capsule. The heat shield survived by destroying itself in a controlled, engineered way that kept the destruction on the outside, but it gets worse. At 18,000 degrees, air does not behave like air anymore. The thermal energy is sufficient to strip the electrons from the molecules, ionizing them, converting the gas into plasma, the fourth state of matter that exists in stars and lightning bolts and the cores of nuclear explosions. And during the 8 minutes of Artemis 2's peak reentry, in a sheath surrounding a capsule carrying 4 people over the Pacific Ocean at 32 times the speed of sound. Plasma is electrically charged, and electrically charged plasma at sufficient density does something to radio waves that ordinary air does not do. It absorbs them, it scatters them, it renders them unable to propagate in the way that communication systems depend on. For 13 minutes during the most extreme phase of re-entry, mission control in Houston could not reach the crew, could not send commands, could not receive telemetry, could not confirm that the 4 people they had been monitoring for 10 days were still alive. The plasma that the speed had created had closed around Integrity like a wall, and the wall did not have a door. In Houston, the screens went blank at 4:14 in the morning Pacific time. The engineers knew this was coming. The blackout was calculated, expected, built into the mission timeline as a known consequence of the re-entry physics. Knowing it is coming does not change what it feels like when the data disappears and the room goes quiet and the clock becomes the only thing left to watch. 13 minutes of silence in a room full of people who had spent years preparing for a mission that was now, temporarily and irrevocably, beyond their ability to affect. But that's not even the worst part. Inside the capsule, the crew was experiencing the physical consequences of shedding 25,000 miles per hour of velocity in 8 minutes. The deceleration generated G-forces pressing into the crew's bodies at peak levels of 4 to 5 times the force of Earth's gravity. At 5G, a person who weighs 180 pounds effectively weighs 900 pounds. The heart, which is a muscle the size of a fist that pumps blood against gravity every second of every day, suddenly has to pump against 5 times that gravity. The lungs, which expand and contract through the action of the diaphragm and chest muscles, are pressed against 5 times their resting weight and must work actively against that compression to draw breath. The blood in the body, being a liquid with mass, is pulled toward the lowest point by the combined effect of gravity and deceleration, and the cardiovascular system works to keep it in the brain and the organs because the brain stops functioning within seconds if the blood supply is interrupted. The astronauts trained for this in centrifuges. They practiced the specific muscle contractions that help maintain blood pressure under high G loads. They had done it before, in training at controlled levels in a machine they could stop. They were doing it now in a capsule they could not stop, surrounded by plasma, under 13 minutes of communication blackout. while the heat shield outside was converting itself into exhaust. The training was the difference between functioning and not functioning, between the crew performing their monitoring tasks and the crew being unable to do anything but endure. They functioned, they monitored, they executed the procedures, and they did it in a physical environment that the human body was never built to inhabit and that engineers had spent decades designing a machine to make survivable. The parachutes deployed at 4:24 in the morning. 11 of them in stages, the drogue chutes first to stabilize the tumbling capsule, then the 3 main chutes blossoming in sequence against the pre-dawn sky, visible from the recovery ships below as something unmistakably good, unmistakably human, a signal that the physics had been survived. The capsule slowed from supersonic to the roughly 17 miles per hour of the water impact. The USS John P. Murtha was positioned and waiting. Recovery swimmers reached integrity within minutes of splashdown. The hatch opened. 4 people stepped into the Pacific morning air and breathed it the way you breathe something you were not certain you would breathe again. At the moment of peak reentry velocity, that air had been traveling from New York to London in 9 minutes, from Los Angeles to Tokyo in under 20, around the entire circumference of the Earth in approximately 1 hour. Not the air of a comfortable flight at 35,000 feet with a drink in your hand and a movie on the screen in front of you. The air of a shock wave. The air of plasma. The air of 18,000 degrees Fahrenheit, wrapping a metal shell around 4 people who had gone to the vicinity of the moon and were coming back through the most violent natural barrier that stands between space and the surface of this planet. 9 minutes from New York to London sounds like the future. It sounds like something that will exist when technology has advanced far enough to make it routine, when hypersonic travel has been engineered into something comfortable, when the speeds that currently require ablative heat shields and communication blackouts and 4 to 5G deceleration loads have been domesticated into something you book through an app. What it actually is right now, today, is a number that describes the single most extreme thing that human beings currently do and survive. Not a